Hey everyone, it's Mr. Riddy back with yet another video. So today, guys, we're going to be talking about our third topic in equilibrium, which is heterogeneous equilibrium. So heterogeneous equilibrium is reactions that, of course, would involve solids and liquids. And solids and liquids are not represented in the equilibrium constant expression as we learned in topic 1. I didn't tell you why then, but I'm going to tell you why now. And the reason for this is that solids and liquids will not expand to the volume of the reaction vessel, and thus the concentration will not change. Therefore, if the concentration of both will depend on their density. Okay, so here's just an image here, guys, explaining that idea. So if you take a look here, the concentration of the solid carbon, the number of atoms per unit volume, is constant as long as some carbon atoms is present. The same is true for pure liquids. For this reason, the concentrations of solids and pure liquids are not included in the equilibrium expressions. So when we would go to write this equilibrium expression for this particular this particular equilibrium here, guys, we're just going to say Kc is equal to the concentration of my product. So CO2 can be included here. You'll notice that it's just the concentration of CO2 over the concentration of CO, carbon monoxide, is raised to the second power. And that would be our equilibrium constant for this particular equilibrium. You'll notice that we did not include solid carbon because solid carbon didn't affect the equilibrium, plain and simple. All right, so example problems, you do, we review. I want you guys to take a moment, pause the video, and write the equilibrium constant Kc for the following chemical equations. Notice that both of these equations, folks, are heterogeneous equilibrium. All right, I hope you were able to get the concentration for number 1 is Kc is equal to the concentration of CO2. You'll notice that calcium carbonate and calcium oxide are not included in this equilibrium expression, folks, because they are solids. And then for number 2, the equilibrium constant Kc is equal to the concentration of chlorine gas raised to the second power over the concentration of HCl raised to the fourth power times the concentration of O2. You'll notice that water wasn't included in this equilibrium constant because water is in its liquid state. Let's keep going. So here's a conceptual problem. For which of the following chemical reactions will Kp equal Kc? So let's take a look here, guys. Remember, for us to have Kp equal Kc, delta N needs to be 0. And the second thing we need to remember is that we're specifically looking for gases, right? Because Kp is about the partial pressure. Okay, so we've got number 1 is sodium. Sodium oxide reacts with CO2 gas to form sodium carbonate plus oxide. If we were to look at our delta N here, we would get delta N would be, again, this has to be 0, so we're going to have 1 from oxygen minus 2 from carbon dioxide, so that's -1, so it can't be A. Okay, then our next one is we have iron 3 oxide reacting with carbon monoxide is in equilibrium with 2 iron solid plus CO2, so delta N would equal from our products this 3 from carbon dioxide and then a 3 from carbon monoxide, so that's 0. Guys, you'll notice that I'm only looking at my gases, again, because we're looking at in terms of Kp. Not to mention, we go back to this idea that the solids in these equilibriums will not have any effect on the equilibrium constant. So I'm not even including the solids in these heterogeneous equilibriums. So delta N came out to be 0. That's why you saw me box off B to be the correct answer. I'll prove to you that B is the correct answer, though. Because if we go ahead and look at letter C, delta N for this one would be 2 plus 1 minus 0, which of course delta N then here is positive 3, which means it can't be C. Again, when I'm looking for these stoichiometric values, when I'm calculating delta N, folks, I'm only including the gaseous equilibriums because, as I've said a multitude of times in this presentation already, is solids and liquid states will have no bearing on the equilibrium constant. And folks, that marks the end of this video. If you have any questions, shoot me an email.